Hello everyone. For today's lecture, I'm going to talk about how we can improve the Rankine cycle to increase the net work output and its thermal efficiency. So please read the chapter 10.4 through 10.6, which is about how we can improve the Rankine cycle, and 10.8 through 9 about the combined cycle and cogeneration. By the end of today's lecture, I really hope that you can answer these two questions. So the first question is, how can we achieve higher thermal efficiencies and also increased power output by combining cycles? And also, how can we make a better use of waste heat? Now, before we talk about the expansion of the Rankine cycle, let's overview what we learned about the simple Rankine cycle in the last lecture. So the simple Rankine cycle is composed of four main key parts. The first one is pump and a steam generator or boiler, and a turbine and a condenser. So through the pump, then we increase the pressure of water, which is a working fluid. And in a steam generator, we have heat added to a working fluid to change the water to superheated steam. And the steam expands in the turbine to generate a power. And after expansion, steam goes back to the condenser, and its phase is changed to water by rejecting heat to the outside. We can draw the TS diagram for these four processes: isentropic for ideal Rankine cycle, isentropic compression, constant pressure heat addition, isentropic expansion, and constant pressure heat rejection. We also can use the first law of thermodynamics for open system under steady state condition to do the ideal Rankine cycle analysis. For 1 to 2 process in a pump, now we know the pump work can be calculated by H2 minus H1. But when you think about the ideal compression process, which is a reversible process, we can also write the same pump work for the reversible process as V1 times P2 minus P1. We usually use this work to calculate the ideal pump work. Then we can calculate the exiting the enthalpy values from the top equation. Now, in a boiler, we also can calculate the amount of heat addition by subtracting H2 from H3. And in a turbine, we also can calculate the turbine work by H3 minus H4. But one more condition that we have to apply is that for the ideal expansion condition, we have to satisfy the isentropic process, which means S3 should be the same as S4. In the last process, which is condensing process, we also can calculate the amount of rejection by calculating H4 and H1. So by looking at those equations, the conclusion is that you have to focus on getting the enthalpy values for every point of your Rankine cycle. Now, based on what we discussed about the simple Rankine cycle, we also discussed how we have to think about the realistic features from the ideal Rankine cycle. But the point here is that now we only have, at this moment, only one pump, one boiler, one turbine, and one condenser. So based on this simple Rankine cycle composition, now the follow-up question is, how can we increase the net power output and possibly thermal efficiency? Okay. So in other words, because we already also understand that the net amount of work can be expressed in terms of the area surrounded by four processes. So this question can be rephrased as this question: how can we increase the cycle area in the TS diagram? So let's think about it, okay? So the first possible way is to lower the condensing pressure, okay, in the bottom. So let's take a look at the TS diagram. So let's say that we have this 1, 2, 3, 4 the starting point, the Rankine cycle's TS diagram, but by lowering the condensing pressure to this point, then we can increase the area by this much. So by the increase of this area, that means that we also can increase the net work. So that is pretty good. But absolutely, there is a limit in doing this way. Okay? So usually, that's why we have condensing pressure below the atmospheric pressure. But at the same time, if you really think about the saturation temperature and how we reject heat from the condenser to the outside, so that saturation temperature, for a lowered pressure, should be still higher than the temperature of the surroundings, like the temperature of river, temperature of a lake, or temperature of the ocean, or whatever that state that you have to make use of. For example, if we have 50 kilopascal as a condensing pressure, your saturation temperature should be 81.32 degrees Celsius. Okay, so that is quite, kind of good temperature there, where we can reject the heat from this temperature to the outside temperature, which is maintained at around like 15 degrees Celsius or 20 degrees Celsius. But you have to think about the temperature outside in order to lower the condensing pressure more and more and more. Having the lower pressure inside the condenser than the atmospheric pressure can cause two problems. The first problem is that because the condenser pressure is always lower than atmospheric pressure, there always a possibility that air can leak into the condenser. Okay, so and if air comes into the condensing, always we have to take this air bubble out, because that can damage all other components inside the steam power plant. So that is one challenge. And another challenge is that by looking at this TS diagram, and if you compare 4 and 4 prime, we can clearly see that quality at 4 prime is lower than the quality at 4. So in other words, at 4 prime, we have more moisture or water droplets inside the steam than 0.4. Then what would those increasing, the water droplets cause or damage overall steam power plant? So these are possible problems of water droplets, going around the turbine. Okay, so even though the water droplets are pretty small, and but still, if you really think about water droplets inside the steam, this water droplet can impact so high to the blade surfaces, and that causes certain corrosion problems or erosion problems because of these water droplets inside the steam. Okay, so now by looking at those blades, okay, and here we can see like huge damage on the blades. And remember, those blades are expensive, so maintenance fee would be huge if you have that kind of problem. So for designing the the Rankine cycle, we have to consider that you have to decrease the content of steam, at the turbine exit as much as we can. Okay, or in other words, the steam quality at the exit of a turbine should be high.